Till our last class, we have already been familiar with the Euclidean space. What basically was the Euclidean space and how to recognize an inner product. From this class, we shall have to be familiar with some terminology, some properties, about some theorems concerning this chapter Euclidean space, which will play a crucial role to solve problems from this chapter. So let us now start. First of all, norm of a vector. Norm of a vector. What does it actually mean? Let us now see. We have considered here a vector space V. That is actually a Euclidean space with respect to this inner product function. That means V is a Euclidean space together with the inner product, this function defined on it. And you already familiar with this notation. In a parenthesis by a single comma, this is actually the inner product function which is defined upon this vector space V, and this vector space V together with this inner product function has become a Euclidean space. And we are considering a vector from this Euclidean space V. We are considering a vector from this Euclidean space V. Actually, in our previous class, we have been defined the inner product, actually real inner product, and we have also considered this vector space over the field of real numbers. That means we are actually litigating with real vector space, and alpha being a vector of V, if we ordered pair, that means if we consider the point alpha comma alpha, this will be from V cross V, that means the domain of this inner product function, and this being a real inner product, obviously this number will be a real number, and we are considering the positive square root of this functional value. The functional value alpha comma alpha under this inner product function is a real number, and we are considering the positive square root of this very real number, and we are denoting it as the norm of the vector alpha, and the norm of alpha notationally is written by this notation, norm of alpha. Clear? Let us now illustrate this norm through an example. Here we have considered the vector space R4. As you already know Rn, and we have restricted the value of n to 4. That means the vector space R4. And we are considering a vector alpha that is equal to 1, 1, 0, 1. This alpha vector being from R4 is a 4 component, remember is a real number 1, 1, 0, 1, as we have considered. The norm of alpha will be the positive square root of the functional value of this ordered pair alpha comma alpha. In fact, we are considering on this Euclidean space R4 the standard inner product. That means this inner product here we have considered as the standard inner product. Try to recapitulate what was the standard inner product. Standard inner product was the component wise multiplication of the vectors of the component vectors forming the point or member of V cross V, and the addition of the corresponding term. And here we have considered alpha comma alpha point. So what would be? So this would be 1 into 1, that is 1 square. Next component is 1. So this is 1 into 1, also 1 square. third component is 0, so this is 0 into 0, 0 square. Fourth component is 1, that means 1 into 1, this is equal to 1 square. After calculating, we have root 3. So root 3 is the norm of this vector alpha. I do think it is clear to everybody. Next, just we shall state a theorem. This is called Schwarz inequality. Schwarz inequality. This is very important. This is very important. Merely you have to remember this statement. The proof of this theorem being beyond the scope of your syllabus. This states that if we consider any Euclidean space and any vectors and two vectors alpha beta, and if we consider the component wise ordered pair alpha comma beta, that means the member of V cross V, the functional value under the inner product which has been defined on this set V, or with respect to which this vector space V is the Euclidean space, the inner product function, the functional value of this point, this member alpha comma beta, and will be, of course, will be a real number, as we are litigating with real vector space, that means a real inner product, and we are considering just the positive value of that real number. Real number may be positive or negative, we are considering the modulus of that very real number, that means only the positive part, magnitude of the real number, positive part, and this will be less than or equal to the product of the individual norms of the component vectors. That means less than or equal to norm alpha into norm beta. Norm alpha is the first component and beta is the second component. That is mod alpha comma beta less than or equal to norm alpha into norm beta. This is called the Schwarz inequality. You have to keep it in your remembrance merely. Okay.